Welcome to the post-class video on Introduction to Thermodynamics and Entropy. And seemed like class went pretty well. Like I said earlier, we kind of have an intuitive idea of entropy and how that relates to the physical world.
Right. And
our task really is to relate that to chemistry in a quantitative way. And so we went through a few things in our first objective. We talked about spontaneity, and what does spontaneous mean?
Spontaneous means that it will happen. If you just let it go, it's going to happen. Yeah,
and it's a little bit different than our kind of general idea of spontaneous, that is just kind of like a spontaneous party, that it wasn't planned.
Right.
Right? In some spontaneous events in chemistry, you kind of have to get them kick-started. Right? Give them a little spark to get going, but once they're going, they keep going on their own. And that's what this net input of energy means in this objective. Right? Spontaneous proceeds without a net input of energy. You don't have to keep putting energy in order to get it to go. So I take my hydrogen balloon and I have to add a spark to it to get it going, but once that spark goes, the rest of the reaction proceeds on its own. For the next important idea was this second law of thermodynamics. It's the law. You can't violate the law.
It's the law.
For any process, entropy increases for the universe.
Right.
Right? And so I'm pretty organized. Tyler is exceptionally organized. That doesn't violate the second law of thermodynamics, because in order for Tyler to be organized, he had to eat tremendous amounts of food.
All the food. And
all this energy went into creating this organized system. Right? So the system's organized, but creating Tyler created a lot of chaos, or chaos? Don't
Not
say
chaos.
That.
Not chaos.
A lot of disorder or entropy in the universe. And that's true for chemical systems. You can have a system where entropy decreases, but for the universe system and surroundings, it has to always increase. And then we looked at a few different kind of parameters. Temperatures. Temperature increases, entropy increases.
Oh, yeah.
States of matter. Solid, less than liquid, gas. There's more freedom for gas molecules.
Yeah, I mean, if I became a liquid, I would have a lot more freedom, and if I was gas, I'd be all over the place.
Right.
So.
Please don't convert yourself to gas. Degrees of freedom, that just means ways of moving. Right? So I can move in a direction, I can rotate, I can wiggle around, do the molecular dance.
Nice.
That's a lot of degrees of freedom, whereas a ball, all it can do is move in different directions. It can't, move my hands in relation to my body. That's degrees of freedom. So more degrees of freedom, more entropy. Right, so for the last piece of activity was maybe conceptually the most difficult, and it has to do with the technical definition of entropy. Is that the technical definition of entropy is that it's really the number of possible states or ways that you can describe a system, or the number of possibilities that a system has available to it. Right? So in class I talked about how in a gas in two flasks, if they're connected, well, the gas molecules can be on one side or on the other side, or they can be spread in between. And if they're spread in between, there's more possibilities for that state. And so that's the most likely state, that's the state with the highest entropy.
Ah.
Right? So it's trying to get a more technical idea of entropy that we can build upon.
Okay.
Hope that summary kind of helps, and we'll see you in class.